You remember when we were creating our 8-bit adder, we said this would be the carry bit which we are interested in its behavior. We are also interested in the behavior of this wire, which is the carry bit carried out of the D3 to D4. And we want to call it the auxiliary carry. Nothing special about it, just like we are interested in the voltage level of that wire and we call it the carry bit, we call this one auxiliary. Now I want to finally complete our ALU. First, this is the abstraction of the previously created parity bit circuit, which says if we have an 8-bit input, this circuit would check the number of ones in this 8-bit value. If we have an even number of ones, this bit would be 1. Otherwise, it's 0. So I call it the parity bit. Next one is this abstraction, which just says this is the most significant bit of the input. We have an 8-bit input and this is the most significant bit of that. We talked about this previously, that we said if the MSB or most significant bit of an 8-bit value is equal to 1, then that means the number is negative, otherwise it's positive. So I call this bit sign bit or sign flag. And I want to put together everything that we have created so far. The combination of 8-bit adder and control nutter and also Cin specifies whether it would have A plus B or A minus B. This is the carry bit, and also we have another bit which we which we call the auxiliary bit. So this input is the A register and this other input always comes from a register called temp. Now this block of nutter, for example, would have its input from the A register, and we talked about this, that if we have CMA, it means complement the A register, which means that the value in the A register which is connected to the input of this nutter would be done, and it would go on these 8 wires as one of the inputs of this multiplexer. At each time, all of these blocks would do one operation and you would have the result of one operation over these output wires. But these 3-bit select bits of the multiplexer would specify which one of the maximum of 8 inputs should go on the output. When one of these 8 bits are on the output, you see every one of these lines are actually 8 wires long. These 8 wires would go through these 3 circuits, which are the important part of this module actually. We have this compared to 0, which we created previously, which one of its inputs is connected to 0. So the only time that the 1-bit output of this compared to 0 is equal to 1 is when the other input is also equal to 1. So when this result of any operation of the output of this combination of multiplexer and gates, which we call the ALU, when these 8 bits are all equal to 0, then this flag would be equal to 1, which we call 0 flag. So this is 0 flag. That's why we say if the result of an operation is 0, then the 0 flag bit is set. This result also goes to another circuit called parity circuit. If the number of ones in this result is even, then this one would be set as well, which we call just parity bit. And finally, we have sign flag, which again is the most significant bit of the same result. So I want to create another abstraction. I just put all of these into another rectangle, right? Another line. And we call this ALU. The ALU takes an 8-bit input called A, which comes from the A register, another 8-bit input called B, which comes from the temp register. We have this Cin and these 3-bit opcode, which specify together whether we have addition, subtraction, not, and all the other things. But the important part is this, and this would have the result, the out. But the important part are these 5 wires: carry bit, parity bit, auxiliary, Z, and sign. How would we use them? Well, first of all, you put an 8-bit register called flags register. Just like any other register, it would have an enable bit and a clock. The clock would go like this, And whenever the enable bit and clock, both of them go high, then what we have is that the input would be written on the output of this flag register. So we would have carry bit, parity, auxiliary Z, and sign here. If you search flag register of 8085, they usually show you something like this, that the bit number 0 is carry, then we don't care, then parity, we don't care, auxiliary, don't care, Z, and sign. But right now, you know how all of these 5 bits come from. I know it took a long time for us to finally get to this lecture, but now you completely understand why is it that we care about these bits. Now, everything that the computer accomplishes is a set of instructions that we call that the ISR of that CPU. The most important instructions of the CPU are jump and call instructions, which those instructions, they look at these wires and would decide what instruction to fetch from the memory. So we have the jump instruction, or JMP-ADDR. What this instruction does is that it would load the 16-bit ADDR inside the PC register. We know that the CPU would jump to the location that PC is pointing to. So whenever we have the value of C3 in the IR register, the 8085 would fetch the other 2 bytes in the memory and load the PC with those contents so that it could jump to that location in the next cycle. Then we have all these conditional jump instructions, which they look at the bits here. The first one is JNZ with the opcode of C2. It looks at the value of Z flag. If this Z flag is equal to 0, then the PC would be loaded by the ADDR or address. You see, when Z flag is equal to 0, just like we explained before, it means that the operation that the ALU has done, these out wires, they are not equal to all zeros. When it is equal to 1, it means that the result is all zeros. So next one is JZ, which is if the Z flag is set, which means again that we had the operation has resulted into zeros. Then we have JNC and JC, which means jump not carry and jump carry. Jump carry means if the carry bit is set, that the result hasn't been couldn't fit in 8 bits and therefore the carry bit has been set, then I want the value of the PC to be loaded with the 16 bit of the ADDR. And we also have all the others. Jump parity odd, jump parity even. They would watch the behavior, the voltage level of the parity wire bit here. And we also have jump positive and, well, JM, I actually forgot what JM means. Well, yeah, it's jump negative or jump minus, which means if the sign flag is equal to 1, then if we have this instruction, the PC value would be, PC register would be loaded with this 16-bit ADDR if that bit is equal to 1, the sign flag. And finally, we have PCHL, which means that load the value load the PC register with the content of HL register pair. You see, everything that the CPU does is to always look at the contents of the PC, right? Fetching the instructions in the memory cell that the PC is pointing to, executing that, and moving to the next instruction. And as you saw, these instructions are the one controlling the value of the PC register, and these instructions would look at the voltage levels of all of these wires here, and we know these wires would all come from the operations that we talked about previously. So as you see, CPU is just abstractions over abstractions. Now in the next lecture, we are going to actually write a simple program to see how the CPU accomplishes its job. Actually, let me just resume it in this lecture. Let's say as a programmer, you have written the values of 3EFA06 and so on in the memory locations of here. if you've been paying attention to what we said, to all the opcodes, or look at the 8085 manuals, we see that 3E is actually the opcode for move I, A, and something. This something would come in the next byte. So this means move I, move the next byte, which comes as immediate value, which is FA in hexadecimal. In binary is 11111010. Put this value inside the A register. So currently A register has this value after executing this instruction. Now we are here. 06 is the opcode for move I, B, and then something. This something is A0, which comes in the next memory cell. So this would put the value of A0 or 10100000 in binary inside the B register. Then it says add B. What add B does is that it says A plus B should be saved inside the A register. We already know that the ALU has one of its input as the A register and another as the temp register. So the CPU would just internally move the value of the B register inside the temp register, then accomplishes the addition, save the result into the A register. So right now the result of the A register, let me check this result, would be equal to 10011010. This would be the new result of A, but this value, the addition of these two, cannot be fit in 8 bits. Therefore the carry bit would also be set to 1. This value, the carry bit, would be 1. So the next instruction says jump carry is zeros, is actually DA. DA is the opcode for jump carry that we talked about here. Jump carry is DA and then 16 bits for the ADDR. So it says look at the carry bit. If it is equal to 1, then jump to the location, to the next bytes that comes after the opcode, which is F000. The order of them has something to do with Indianness. So jump carry, which always says that lower byte comes at the lower address. So this is the lower byte comes here, then the higher byte at the higher address. So we have jump carry F000 in hex. So it checks the carry bit, but the carry bit has been set because of the previous instruction. Therefore, the value in the PC register would be loaded by the address of F000. And for that, now the PC doesn't point to this location. It would point to the F000, which is here, and the opcode in it is 2F, and 2F is the opcode for CMA, or complement the result of the A register. And A register is currently this value, so it would be complemented, therefore 10100110. This would be the new result, the new value, or the value in the A register because of the program that we executed here. I just wanted to show you how a simple program would be done and how 8085 would check different wires based on different operations.